You know when you look at a chemical formula and it just seems like a random jumble of letters and numbers? Well, what if I told you it's not random at all? It's actually a language, a secret language that tells the story of everything around us, from the water we drink to the air we breathe. And today, we're going to learn how to read it.
So let's kick things off with a little puzzle. Imagine you mix some baking soda and vinegar in a flask, and you pop a balloon over the top. The balloon blows up, which is cool, but here's the weird part. If you look at the scale, the weight doesn't change one bit. But then, you take the balloon off, and suddenly the weight drops. So where did that mass go? Did it just vanish into thin air?
To solve this mystery, we need to put on our detective hats and follow the clues. And the first step is to really understand what's going on inside that flask when all those bubbles start fizzing up. Okay, let's dive right in. All right, so here are the facts of the case. We start with our two ingredients, or reactants, as scientists call them. First, we see bubbles. That's a huge clue right there, telling us a gas is being made. Second, the total weight stays the same as long as that balloon is on tight. But third, the moment we let the balloon go, the weight goes down. That's our smoking gun. Something invisible was created, and it was trapped inside that balloon. Now, to describe what just happened, scientists don't just write, baking soda and vinegar make bubbles. No. They use this incredibly precise and powerful language. And to solve our mystery, we've got to learn the basics, starting with its alphabet. The alphabet of chemistry is basically the periodic table of elements. Every single element, the basic building blocks of all matter, gets a 1 or 2 letter symbol. H for hydrogen, C for carbon, Na for sodium. Simple enough, right? These are our chemical letters. And just like in English, when we combine these letters, we start to form words. In chemistry, we call these words chemical formulas. And a formula tells you the exact recipe for one tiny little unit of a substance. So let's quickly break down how to read these chemical words. See that tiny number, like the 2 in H2O? That's called a subscript. All it does is tell you how many atoms of the element right before it are in that one molecule. So H2O means 2 hydrogen atoms and 1 oxygen. If you don't see a number, it just means there's one of them. It's basically an ingredient list for a molecule. Okay, we've got our letters, we've got our words. You know what comes next, right? We're ready to write a full story. In chemistry, that story is called a chemical equation, and it describes exactly what happens during a reaction. Every story has a beginning and an end. It's the same in chemistry. The beginning has our reactants. That's all the stuff you start with. And the end has our products, the brand new things you create. Reactants on the left, products on the right. Simple as that. And the grammar is super consistent. You write down the formulas for your reactants, you put a plus sign between them if there's more than one, and then you draw an arrow. That arrow is the action verb of the story. It means reacts to form. And after the arrow, you just write down the formulas for all the new products. Now, here's the thing. This chemical storytelling has one very, very important, absolutely non-negotiable rule. And it's not just a rule for your chemistry class. It's a fundamental law that the entire universe has to obey. So what this means is you can't just make atoms appear out of thin air, and you can't make them vanish either. All the atoms you start with have to be there at the end. They just get rearranged into new combinations. Think of it like a set of Lego bricks. You can take them apart and build something totally new, but you still have the exact same number of bricks you started with. And because of this universal law, every single chemical equation has to be balanced, just like our scale from the beginning. This is it. This is the final clue we need. It means the number of atoms for each element on the left side of that arrow has to perfectly equal the number on the right side. It's like a perfect accounting system where absolutely nothing gets lost. And this table shows that rule in action beautifully. Let's look at the equation for burning methane, which is natural gas. If you do a quick count, on the left, we start with 1 carbon, 4 hydrogens, and 4 oxygens. And on the product side, 1 carbon, 4 hydrogens, and 4 oxygens. Exactly the same. The atoms just switched partners, but everyone is accounted for. The books are perfectly balanced. All right, detectives, we have the language, and we have the universe's biggest rule. It's time. Let's go back to our flask and finally solve the mystery of the vanishing mass. And here it is, the full chemical story of our experiment. On the left are reactants, baking soda and vinegar. And on the right are 3 new products, sodium acetate, water, and carbon dioxide. You can see how nothing is lost. Every single atom from the start is now part of a new molecule. Okay, now let's zoom in on those products. We've got two liquids, but hold on, look at that third one. Carbon dioxide, CO2. And what do we know about carbon dioxide? It's a gas. It's the same stuff that makes your soda fizzy, and it's the very same gas that was making all those bubbles in our flask. And there's our solution. Case closed. The mass never vanished at all. It was converted into a gas, that carbon dioxide, which filled up the balloon. As long as the balloon was trapping the gas, its mass was still on the scale. But the moment we took that balloon off, the gas escaped into the air and its mass just floated away. The law of conservation of matter was never broken.
Okay, so we solved a neat little puzzle, but so what? Beyond that, why is understanding this chemical language and its big rules so important?
Well, here's the really big idea. This isn't just about fun experiments. Chemical equations are literally the recipes for how our entire world works. And the law of conservation of matter is the one rule that all those recipes have to follow. It's happening when a cake bakes and becomes something new, or when a piece of iron rusts. It's happening inside of you right now, as your body rearranges the atoms from your lunch to give you the energy to watch this. In our universe, nothing is ever truly lost. It just becomes something new.
So the next time you see something change, a leaf turning brown, a campfire burning, an Alka-Seltzer tablet fizzing in water, remember that you're just watching a chemical story unfold. And now you know how to start reading the language it's written in. Thanks for watching.